Thermite was first invented in 1893 and patented in 1895 by Hans Goldschmidt. The reaction has also been called the Goldschmidt process. It is a type of aluminothermic reaction in which the aluminum metal is oxidized by the oxide of another metal, most commonly iron oxide. The thermite reaction has been employed to extract metals such as iron, chromium, vanadium, nickel, and copper from the respective oxide ores. A modified version of the thermite reaction was used to extract the uranium in the Manhattan Project at Ames Laboratory. The thermite reaction has also been used by the military in incendiary devices to quickly destroy or disable equipment. Thermite has also been used for on-site welding in places where it was difficult to bring in heavy welding equipment. This demonstration illustrates the reaction between iron-3 oxide, commonly known as rust, and aluminum metal. The products of the reaction are aluminum oxide and elemental iron. The reaction is extremely exothermic, producing 851.5 kilojoules of energy per mole of reaction. This is enough energy to reach temperatures in excess of 3,000 degrees Celsius, high enough to liquefy the iron. Although the thermite reaction is extremely exothermic, the reaction will not take place at ambient conditions. This is because the activation energy required to initiate the reaction is very high. The reactants lack the necessary energy to initiate the reaction. The reaction between glycerin and potassium permanganate will be used to provide the needed energy to initiate the thermite reaction. Glycerin is readily oxidized by permanganate, forming manganese-3 oxide, carbon dioxide, potassium carbonate, and water. The reaction is exothermic, producing enough energy to enable the thermite reaction to take place. The activation energy for the reaction between glycerin and permanganate is quite low. As you will see, the glycerin and permanganate react when they come in contact, slowly at first, but as heat is generated, the reaction rate increases rapidly, producing enough heat to ignite the glycerin. A mixture of iron-3 oxide and aluminum powder has been placed in the clay pot. Potassium permanganate has been placed in a small indentation at the top of the mixture. Glycerin will be added to the permanganate. The energy produced by the oxidation of the glycerin will ignite the thermite reaction. The oxidation of glycerin and the thermite reaction clearly illustrate the effect the magnitude of the activation energy has on the rate of reaction. The activation energy for the oxidation of glycerin is low enough that the reaction can take place at ambient conditions, while the thermite reaction cannot. In general, one can conclude that the higher the activation energy, the slower the rate of reaction. I'm now going to demonstrate another version of the thermite reaction. I have 2 iron balls, both of which are partially rusted, and one is covered in aluminum foil. All of the reactants needed for the thermite reaction are present. All that is needed is the activation energy. I'm going to provide the activation energy by striking the 2 together. As seen in this video, there is an energy barrier that must be overcome for a chemical reaction to take place. All reactions have this barrier. In some cases, the energy required is low, as in the oxidation of the glycerin by the permanganate. In other cases, it's high, as in the thermite process. In general, the higher the activation energy required for a chemical change, the slower the rate of reaction.